All right, we are up to lesson 14 now of Unit 7. So let's go right into the examples. Researchers want to know the effect of captively raising birds on the weight of the birds. So the researchers begin with 100 birds divided into two groups of 50 each. One group of 50 will be raised in captivity, and the other 50 are tagged and released into the wilds. After 500, all 100 birds are collected and weighed. There are more than 10 to the 29th different ways, and to give you an idea of what that means, 10 to the 29th means is a number of 1 followed by 29 zeros. So it's a pretty gigantic number. So there are more than 10 to the power of 29 different ways to regroup the 100 birds into groups of 50 again. So looking at all the combinations would be too time consuming to reproduce. In this case, we can run simulations to determine how the original difference in means compares to those from regrouping the data. The original groups have a difference of means of 0.27 grams. Researchers run 1,000 simulations, regrouping the data into two groups at random and recording the difference in means for the groups in each simulation. The histogram shows the differences in means from the simulations. Okay. They determine that the mean differences of means from the simulation is 0.0021, and the standard deviation for the differences of means in the simulation is 0.112. Okay. What features of the distribution in the histogram let you know that modeling with a normal distribution is reasonable? Well, if I look at here, is it roughly symmetric? Yes. Is it bell-shaped? Roughly bell-shaped? Yes. So it's symmetric. So what features give it away that I can model it with a normal distribution? It's symmetric, it's bell-shaped, and it's unimodal, meaning it has one high point up here. Okay. Number 2, model the simulations using a normal distribution with a mean of 0.0021 and a standard deviation of 0.112. What is the area under this normal curve that is more extreme than 0.27? Okay. So you might remember from a previous lesson when we talked about normal distributions. I believe it was lesson 7. Okay, we talked about how to find percentages using this online calculator here. Okay, and the online calculator again looks like this. Okay. So our mean in this case, and we're going to use this to find the answer to number 2. So our mean was 0.0021. So 0.0021, and our standard deviation was 0.112. And we want to know the percent or the area under the normal curve that is more extreme than 0.27. So more extreme would be above 0.27. And if I calculate, I get an answer of 0.0084. So 0.0084, which is 0.84%. So it's less than 1%. Okay. How can this area be used to compare the differences of means from the simulations to the differences of means from the original group? So what this is telling me is that 0.84, so 0.27 is about right here. So 0.84% is greater than 0.27. But remember, I could also have a negative difference. So negative 0.27 is here, anything less than that. So anything less than negative 0.27 would also fall under this here. So if I wanted to find the total, because of the symmetrical nature of the histogram, I could multiply 2 times 0.84. So 2 times 0.84 is 1.68. So what this is telling me, okay, what this is telling me is that 1.68% of the simulations have a difference in means greater than the original difference, which was 0.27. So only 1.68% of the simulations resulted in differences of means that were more extreme than the original 0.27 grams. Okay? Based on the area under the normal curve, is there evidence that the original difference in means is likely due to where the birds spent the 5 years? So because a very tiny amount, less than 2%, so less than 2% of the simulations resulted in differences that were more extreme than my original difference of 0.27, then that means that yes, that the original difference was due to where they spent the 5 years. So yes, because 1.68 is such a small percentage. Okay? Now let's say I had done this and let's say it was 21.68%. Say it was 21% or 25% or 35%. Let's say 35% of the simulations resulted in differences that were more extreme than 0.27. Okay? Then the answer to number 4 would have been no. Okay? But because only 1.68% of the simulations resulted in differences that were different from what we got, well, then we can assume that the original data we took, that it was good results. Okay? Again, if I had gotten, say, 25% or 35% or 45%, which is a much larger number, then chances are there were problems with how I set up the experiment. But because I got a very small value of 1.68%, I can pretty confidently conclude that the original difference was actually due to whether they spent the 5 years in captivity versus in the wilds. Okay, and that's what they were going for in that particular question. So that is it for our examples, and that is it for this lesson.